Okay, so good evening, everyone. Welcome to the last live session, that is the live session relevant to the contents of week 12 for this NPTEL course on fluid mechanics. Uh, I hope my screen is visible. Ragul?
Yes, sir. Yes, sir.
Okay, fine. So, Ragul, as far as I remember, you have sent one mail actually today, and yes, we had a
Yes, sir.
discussion related to this mail last week. Anyways, so today I will start with your doubts. Okay, I will start with your doubts because I'm not feeling that well. So I don't want to miss the questions or I don't want to miss the doubts that you have raised. So first of all, we'll be
Okay, sir. No problem.
yeah, I'll be discussing your doubts and then we'll move to today's content. Okay. Okay. So the first
Sure, sir.
question, yeah. So the first question, I have downloaded the document that you have attached in the mail that you have sent me. So why the centripetal acceleration is taken as AR equal to minus R omega square. I think this is your doubt, right? Means how this expression came into picture. Is it?
Yes, sir.
Okay,
Yes, sir.
fine. So acceleration A for a circular motion, what is the expression according to you? Means you must have
Omega square into R.
that no yes, omega square into R is here, but uh, your doubt is how this expression came, right?
Yes, sir. I don't have doubt with that. But why that minus sign?
Yeah,
I
why
have
that
doubt in the
minus
only
sign?
in the
Yeah, why
convention. That's what.
why is that negative sign is there? That is your doubt, right?
Yeah. Yes, sir.
Yeah,
Yes.
so it is basically the sign convention. Now the standard convention that is being followed, see, whenever you consider a circular motion, okay, whenever you consider a circular motion, so this is the tangential velocity. Okay, now suppose if this is rotating, say this is the point through which the axis of rotation is passing. Okay, find this point, say I'm
Okay, sir.
calling this point A. Now when the acceleration, see, there are two types of acceleration in circular motion. One is your centripetal acceleration, another is the centrifugal acceleration. Okay,
Okay.
yeah. So what is the difference between these two? The difference between these two is one acceleration, that is centripetal acceleration, directed directed
Towards center.
towards the axis of rotation or towards the center, this A. Okay, and centrifugal is directed away. So it is basically a sign convention. Now the thing is, if you don't give this negative sign, no problem, but from the very beginning of your derivation, just one second, just from the very beginning of your derivation, you need to follow that convention. That is the only thing. Okay,
Okay, sir.
yeah. But the thing is, uh, in any standard reference book or textbook that you follow, you will find that the general convention, see, uh, if you can consider the case of, our Cartesian coordinate system, right? In Cartesian coordinate system, what is the procedure? We are considering this as positive x, this as negative x, this as positive y, this as negative y, right? Negative y.
Yes, sir.
Yeah, but there is no harm. Okay, there is no harm if you consider this as negative and this as positive, this as negative and this as positive, or anything. Okay, but the thing is, whatever you are deriving, okay, whatever you are deriving, it should be according to the convention that you are following. It is only a convention. There is no hard and fast rule.
Okay.
But since this, we always take the right hand side along the horizontal as the positive x-axis and the left hand side this direction, okay, as the negative x-axis. This is the standard which is being followed by most of the say institutions or maybe the standard books. So in order to avoid some additional confusion, we follow a standard convention throughout. That is the only reason. Clear?
Okay, sir.
Yeah, okay. So next is your, if I remember, yeah, this particular expression, right?
Yes, sir.
Yeah, this particular expression, for this I have already downloaded one picture because for me drawing this picture will be a little bit difficult because I don't have that sophisticated drawing tools or something. So this is a typical uh, say, I will say a chunk, a typical chunk, not this, this is a typical chunk from a r theta z coordinate system. So r theta z coordinate system is generally known as a cylindrical coordinate system. Okay.
Okay.
Now if you consider this volume, okay, this volume, the volume means this shaded portion, you are like, is it clear, the shaded portion, the portion in brown?
Yes, sir. Yes, sir.
Yeah, so one of the length is r d theta, the other one is dr, and the dimension or the thickness along z direction is dz. Okay, so why this is r d theta, why this is dr, let me explain. See, if you consider in 2D,
Yeah, that I
yeah, that you have understood,
understood
right? Yeah, let
from
me,
planar.
yeah, fine. Now see, if you consider this phase, okay, now don't look at this expression, you forget this expression, because this is, I think, for the case of mass conservation. But you consider, if you
Okay.
are for this particular control volume, if you are considering that the only external force that is acting on this particular control volume is the pressure force. Okay, then what is this direction?
Yes.
Direction represented by
That is
this arrow,
mass.
it is the r direction.
Mass.
Yeah, r direction, right?
Yes, sir. Yes, sir.
Yeah, so for r direction, say for this particular phase, okay, this particular phase, say the pressure is, say something, say I'm writing p. Okay, and what will be the pressure on this phase? It is, say, because we have moved a distance delta r, so based on that, one second, so based on Taylor series expansion, suppose this is p plus dp. Okay, so what is the net pressure force that is acting on this volume? What is the net pressure force? The net pressure force that is acting on this volume is P,
Difference between the
yeah, minus P plus dP, but this is the pressure. So for getting force from
multiply
this
with
pressure,
area.
you need to multiply this with area.
Area.
Yeah, so
Yes,
the
sir.
area, sorry, the area should be r d theta, because if you consider a elemental volume, this can be approximated as a straight line. So r d theta into dz, clear?
Yes, sir.
Huh.
Yes, sir.
So r d theta dz. Okay, so from this you are getting minus of dp r d theta dz. Now dp should be equal to what? Along r direction it is del p by del r dr, right?
Yeah.
Yeah. So this is one part. The other part is, now this net, see, if you again recall Newton's second law of motion, the net external force or the net force acting is equal to or is responsible for uh, creating some what?
Mass into acceleration.
Acceleration. That is the inertial force that we have discussed in the last class in your doubt session only, right?
Yes, sir.
Yeah,
Yes,
so
sir.
what will be the mass for this particular volume? What will be the mass? So mass will be density into volume, right? So the
Yes,
volume
sir.
is r d theta dr dz. Clear?
Or dear. Yes, sir. Yes, sir.
R d theta means this one into dr into dz. Okay, means three dimension.
Correct.
Yeah, so this is
Yes,
only
sir.
the mass part. And what will be the acceleration? Acceleration will be ar, because we are considering the r direction. Okay,
Yeah.
yeah,
Yes, sir.
so that should be equal to whatever. See, the convention is not means it's definitely important, but if you for the time being ignore the convention, so you will be getting, see, this rho rw square is nothing but rho ar, and this is del p by del r, as we have seen in the other expression. Clear?
Okay.
Yeah, so this is how you are getting this, and similarly these expressions also based upon the assumptions that were taken. Clear?
Okay, sir.
Yeah. Next is, your next question is, what is uniform flow, right?
Yes, sir.
Yeah, so what is uniform flow? See, uniform flow is a flow where the velocity, okay, the velocity field or the velocity, see, the velocity field is defined by three components. If you consider a generalized case, if you consider a generalized case, the velocity is defined by, the velocity field is defined by three components. One is the component along x-axis, the other one is the component along y-axis, and the third one is the component along z-axis. So we normally represent it by u, v, and w. Okay. So when this velocity, okay, is not changing at a particular instant of time from section to section, okay, when suppose at a particular time instant, say I'm calling it t1, at a particular time instant t1, the velocity at section 1, at section 2, at section 3, the velocity distribution of the velocity field is same, then we call it uniform. Okay.
Okay.
Yeah, it is only with respect to space and only the velocity component. Clear?
But it may change with time, sir.
Yeah, it may change with time. Means if it changes with time, then it will be unsteady uniform. If it does not change with time, then it will be steady uniform.
Okay, so along the direction of the flow, it should not change.
Yeah.
Velocity should not change.
Along spatial
It's
coordinates, it
what
should not change. Yes.
whether it is received only for velocity or if that
No,
both apply for temperature also.
no. When we are telling uniform flow is basically it signifies only the velocity. Unlike steady or unsteady, in steady, unsteady, actually it is for any flow parameter. Okay. But when you say
Okay.
uniform, it is only for velocity. And suppose you are telling, suppose you are saying that it is uniform in terms of temperature distribution, then you call it the temperature distribution is uniform. But when you say that the flow is
So you
uniform, it's
feel at the
huh? Yes, Ragul. Ragul. Hello,
hello
Ragul.
sir, can you hear me sir?
Yeah.
Yes sir. Suppose if we say the flow is uniform, then whatever velocity at the inlet, the same velocity will be pertaining throughout the flow, sir.
Yes. But
There is no any kind of there is no any parabolic kind of profile,
yes,
whether it
yes,
says like
yes,
that.
yes. But the thing is, we say that the flow is uniform. The flow is uniform. Say we're calling it x direction. Then we say that the flow is uniform along x-axis. Okay. We are not telling that because if suppose this is the z direction, say this is the z direction, the flow is not uniform along z direction because along z direction variation is there, right? If we if you consider these points, then the velocity is different, right?
Yeah, yes sir.
Yeah.
Along
So
Z it is different.
yeah, and so the flow is non-uniform along z direction, but it is uniform along x direction.
Okay, okay.
Yeah, but if your velocity distribution, say there is a hypothetical case, if it is something like this, okay, if it is something like this, if it is something like this, okay, then we say that the flow is uniform along x direction as well as the flow is uniform along z direction. Clear?
Okay.
Yeah.
So,
Huh.
but uh, textbook says that along uniform flow, the momentum correction factor beta, right? That will be one. It's given in that case.
Momentum correction factor beta will be equal to 1 for
Yes, uniform flow like that they mentioned. Then how it will be? How can we justify that? Because the velocity profile is parabolic, right? Then it is allowed to be parabolic also.
see if it is parabolic. See for I'm just actually one second. Yeah, now I am just writing one thing. Okay, here let me just look carefully. As I told you, I do not have the resources, so momentum correction factor for
Yes.
circular, sorry, circular pipes. Okay, now see, it is around 1.33, not exactly 1, because the effect of the this parabolic effect is, see, what is the expression for momentum correction factor? What is the expression for momentum correction factor? The expression for momentum correction factor is Hello, Raghu.
Yeah, actually,
Ah,
it's a it's a ratio of momentum based on actual velocity by momentum based on average velocity.
average, yeah. So let us say this one. Okay, let us take a page here. Yeah. So you see, it is equal to 1 if you consider only this one. Okay, you can derive it, no problem. Say there is a velocity distribution something like this. Okay, there is a velocity distribution something like this. Okay, it is means a perfectly rectangular variation. Okay, everywhere say the velocity
Okay.
is u. Okay, so for this case you simply derive the value of beta and you will find it is 1. But for
Yeah,
parabolic
in
case
this
it is
case it will be equal to 1.
yeah, this case it is 1.
Yes, that's what I
Yeah,
doubt.
yeah, for this case it will be 1.
Okay, sir.
Yeah. So then, yeah, what is the physical meaning of characteristic length? Yeah, I have this particular question is very interesting, and this is not a very simple question. Okay, this is not a very simple question, and it is good that you have raised this question. uh, why for a pipe we choose it as the diameter as the characteristic length, then why not the length of the pipe, then why characteristic length for flow over a flat plate is chosen from the distance from the leading edge, right? Why not the width? So these are very
Yes,
interesting
sir.
question. Now the answer to this question is, it's like you'll have to imagine. Okay, you'll have to imagine. Now why you have to imagine, let me tell you. See, first of all, the fluid mechanics that we are studying, or the solid mechanics that we are studying, with the purpose of, say, designing civil or mechanical engineering systems. Okay, so we follow a very important assumption, and that assumption is continuum, right, Ragul?
Yes, sir.
Yeah. So you have heard
Yes, sir.
about
Yes, sir.
continuum. Yeah. So what is the meaning of this continuum? The meaning of this continuum is, though at the molecular level, the
Discontinuous, we assume functions to be smooth continuous like
yes,
that way.
yes, yes. We consider the various distribution, the various properties to be continuous and smooth. What is the meaning of this? The meaning of this is that suppose we are writing that, say, density. Say we are writing that density is a function of x, y, and z. Okay. It means that density is a function of x, y, and z. It means that there is a one-to-one correspondence. There is a one-to-one correspondence between the physical space and this density function. Means for all the combinations of x, y, and z, which represent a spatial point in 3 dimensions, there is a specific value of density or maybe any other property, right?
Okay.
Yeah. Now, how do you decide whether for a particular problem, uh, the continuum hypothesis will be valid or not? So for that, there is a thing called Knudsen number, Kn. Have you heard about this Knudsen number?
Yes, sir. It should be less than very less than 1.
Yeah, but what exactly is this Kn? What is the definition of Kn?
Characteristic length by that
No,
lambda, sir.
lambda by
Lambda by L,
L, where lambda
LC.
is the mean free path, L is the characteristic length, right?
Yes,
Now,
sir.
what is mean free path? Mean free path is, we know that every object, due to the virtue of its temperature, all the molecules of that object bear some energy owing to its temperature. That is the thermal energy, right? And they are
Yes, sir.
constantly vibrating and they are moving. Now, the minimum distance or the average distance traveled by a particle, okay, in a medium before it collides with another particle, okay, that is the mean free path,
Mean free path.
right? Now, you have told a very important limitation, not limitation, basically a limit. Knudsen number, if it is, what you said, if it is less than,
Yes. Point 1.
just one second. Yeah, if it is less than zero point 0.1, you are saying that continuum hypothesis is not valid or valid.
Less than 1. Valid, valid.
Mm. So if it is less than zero point 0.1, then continuum hypothesis is valid. Now, basically, if you generalize, okay, you forget these values. Okay, you forget these values because depending upon certain problems, these values may change. Okay, And how you determine those values, there is a different actually field. There is a concept of REV you must have studied about, representative elementary volume. So you can perform experiments, you can come make it, you can arrive at these values from like these values may differ from situation to situation. But the crux of this discussion is when the Knudsen number is less, continuum hypothesis is, when the Knudsen
valid,
number is less, it is,
valid.
yeah. So the Knudsen number is less means what? Less means either your mean free path is very small or your characteristic length is very large,
Characteristic length is very large.
right?
Yes, sir.
Yeah, either the lambda is very small or L is very large. Okay. Now, if lambda is very small, it means that the like you cannot directly say that, but you can imagine something like this, that the particles are, means lambda is very small means what? After traveling a very small
First,
distance, a very small average distance, the particles are colliding. It means that they are very closely packed, and if they are closely packed, there is a better chance of getting that one-to-one mapping or the bijection that we are talking about in the continuum hypothesis, right?
okay.
Yeah. Now let us come to your question, that why, how do you decide the characteristic length? The characteristic length, the decision of a characteristic length is not that simple. For that, there are different ways. Okay. Now, in case of pipes, we consider it as the diameter of the pipe, or you can consider the radius also, no problem. In case of open channel, we sometimes it is considered as the top width, sometimes the hydraulic mean depth or the hydraulic radius. Fine. But in order to arrive at a particular quantity as a characteristic length or maybe any characteristic property, you need to perform a lot of experiments. Okay, you need to perform a lot of experiments. You need to perform a lot of experiments, and based on the result of the experiment, you need to see when you are performing the experiment, why you are doing the experiments, or why, or you can perform the experiments maybe in labs, or maybe you can perform some computer simulations. But at the end of the day, we expect some results, means these experiments, either numerical or laboratory experiments, they will give you some results. Now how much these results are agreeing with the actual values that are expected. Okay. Now, for example, you want to do some experiment or you want to do some study related to pipe, you can consider the length of the pipe, you can consider the length of the pipe as your characteristic length, no problem. Okay, suppose you are designing a pipeline system or a network of pipeline, and you are considering the length of the pipe, the total length of the pipeline as the characteristic length, no problem. Now, after doing that, if the results that you are obtaining is not matching with the expected outcome, then what you will do, you will change this characteristic length. So there is basically different ways you have to perform experiments. Sometimes it comes with experience. Okay, so it is not a very straightforward answer. And this characteristic length, maybe the second part that we have asked, for a flat plate it is chosen as the distance from the leading edge. See, these results were not arrived at in a single day. Lots of experiments were performed. Based on these experiments, now you must have remembered that whenever you study boundary layer theory, the Reynolds number is basically defined as Rex. Okay, so what is X here? X is basically the distance from the leading edge. Okay, now see, somebody might have taken the width of the plate as we have asked in the question. They might have taken, but after that they must have seen that whenever you consider the width of the plate and you calculate the Reynolds number, okay, by considering the width of the plate, they have not obtained a good result, and that's why after a lot of trial and error, uh, this X or D or these things were arrived at. Okay, so basically the crux of your question is, the crux for your doubt is that whatever characteristic length you choose, you have to keep in mind that that length should be representative of the entire system. Okay, it should be able to represent, it should be able to uh, basically reproduce the engineering effects that we are expecting. Okay, it may not come in a single
Okay.
blow. Is it clear, Ragul?
Yeah, yes, sir.
Yeah, fine. Your next question, what is the reason behind the non-dimensionalization of equation of
So,
yeah,
sir, the reason for choosing length as So diameter as a parameter instead of length in case of pipe is only to take into account of it's purely come from experimental, sir.
Experimental plus there are some intuitions also. Let me tell about that. Okay, suppose there is a pipeline which is say 1 kilometer long. Okay,
Okay.
fine. Now it is a fully developed pipe flow. If you consider any cross section, say it is a laminar flow. Let us consider it is a laminar flow. So this is the velocity distribution. Fine.
Okay.
Yeah. Now see, if you compare the entire length, say L, and the cross section, say this is the cross section, the circular cross section A, where are you expecting more changes for a fully developed pipe flow? Is it along the cross section or is it along the length?
It's along the length.
Why along the length? Because it is a fully developed flow, the velocity is not changing, right? But if you consider a particular section, then velocity is changing, and that is of more interest to you.
Yeah.
Yeah, had it been a developing flow, then uh, it is not that straightforward. Okay, we'll have to keep so many things in mind. But that's why I told you it's a fully developed flow. Okay, so for a fully developed flow, more changes are expected along a particular section. Okay, not along the length. But yes, if you think in terms of the head loss HF and all, but for head loss HF, okay, if you remember, we have already taken into consideration the length, the Darcy-Weisbach equation,
Yes,
right?
sir. Yes, sir.
Yeah, but the characteristic length is something which is representative of the entire system. Now see, this length is not representative. Why this is not representative? Suppose I do not want to study the entire stretch. I want to study only this much. Okay.
So you suppose our intention is to study only about fully developed flow.
Yeah. Suppose see what is the definition of Reynolds number? Definition of Reynolds number is rho v L by mu, right?
Yes, sir.
What is this L here? This L is the characteristic length.
Yes, sir. Yes, sir.
Yeah. Suppose you want to study this pipeline. Okay. Say only for its length L1. Okay, not the entire length, say L1. So for that your Reynolds number will be L1, right?
Yeah.
Huh.
Yes, sir.
But suppose you want to study only say another stretch, a short stretch whose length is L2. For that the Reynolds number is rho v L2 by mu. Okay. So this Reynolds number will be smaller than this Reynolds number, right?
Yes, sir. Yes, sir.
If you consider the entire length of the pipe, say it is rho VL by mu, that will be the highest Reynolds number. So see, Reynolds number is also changing. But for a fully developed pipe flow, if it is a horizontal pipe, okay, of uniform cross section everywhere, then the Reynolds number is fixed, rho VD by mu. So that is more realistic, right?
Yes, sir. Yes, sir.
Yeah. So see, there are many things that you need to keep in mind.
Okay.
Clear? Means this is just for an example I have given. Clear?
Yes, sir. It's actually taken only based on the effect or experimental studies to
No,
study
sometimes
the.
it is experimental studies, sometimes it is a combination of your intuition plus experimental studies. Sometimes
Okay.
yeah, means there is no single correct answer. Means it varies from situation to situation. Okay.
Okay.
Hmm. Sorry. So can you move to the next question?
Yes, sir.
Yeah. So what is the reason behind the non-dimensionalization of equations? Yeah, this is a very simple equation. No, sorry, simple question. What is the physical meaning of scaling parameters that are used in a non-dimensional equation motion? How to choose the scaling parameters? Yeah. Non-dimensional Navier-Stokes equations. Okay. Yeah. So these equations are visible, right?
Yeah, yes, sir.
Yeah. So see, for your first question is, what is the reason behind non-dimensionalization of the equation? And your second question is, what is the physical meaning of the scaling parameters? Okay. Now see, in in Navier-Stokes equation, what are the parameters? It is the velocity field UVW, the pressure field P, right? The dependent
Yes, sir.
parameters, and your independent parameters are the space and time coordinates. Okay. So when you have in the dimensional form, means when you have not done the scaling, UVW represents the velocity field, P is the pressure field, XYZ, and T represent the space and time coordinate. Okay.
Yes, sir.
Yeah. Now, if you what happened? Just 1 second, huh?
Okay, sir.
Just 1 second. Power mode plugged in. Just 1 second. My battery is. Yeah. Please excuse me for a second. Okay. Fine. So, if you look at the non-dimensional form of this Navier-Stokes equation, here this U, V, W are basically all the non-dimensional velocity. Okay. Or let me take a better form because you might get confused. Anyways, but forget it. See here, this U, V, W are not this U, V, W that you have written. Say the non-dimensional form of these are U star, V
Okay,
star.
sir. I understand.
Yeah, you understood now? Okay. So,
Yes,
if
sir.
that is the case, you look at this equation. These are all non-dimensional parameters. Which parameter is of only physical significance here? The parameter that is of only significance is the Reynolds number.
Yeah.
Yeah, right? So what you are doing, see, Navier-Stokes equation is a very complicated equation to solve if you are solving it in its most general form. In fact, there is no exact mathematical solution to the most generalized form of the Navier-Stokes equation, and that's why the current trend is to solve this Navier-Stokes equation numerically, which is a separate branch of study which is known as computational fluid dynamics. Okay,
Okay.
yeah. So
So
that
CFD is used only to solve Navier-Stokes equation, sir.
see, not only Navier-Stokes equation, there are different equation, but I am giving you an example.
Okay.
Okay, means if you non-dimensionalize the parameters, your number of dependencies reduce, and basically the entire problem get fixed to a single physical parameter. Okay, for in Navier-Stokes equation, it becomes Reynolds number. And if now see, in this particular form of Navier-Stokes equation, we have neglected the body force component, right?
Yes, sir. Yes.
Yeah. Now, if you neglect the body force, if you do not neglect the body force component, if you,
Froude's number will come.
yeah, Froude's
Froude's
number
number
will
will
come.
come.
Yeah, that is the thing. Then,
So
huh,
suppose initially we had independent parameters like dependent parameters like u, v, w,
huh,
and dependent parameters like x, y, z, and t.
yes,
If
yes,
we non-dimensionalize, we are turning into form of photo only one parameter, like that you were saying,
yes,
like
yes,
Reynolds
physical
number only
parameter.
Froude's number like that.
Yes, 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 yes. You will get a
So
very
thereby we reduce the variables,
we reduce
reducing the
the
variables.
not exactly the variables. Variables are there, but we reduce the physical dependency. Okay, variables are there.
Physical dependency.
Yeah, physical dependency. See, earlier, if you take the entire Navier-Stokes equation, okay, suppose in dimensional form, what happens? U, V, W, P, everything has a certain meaning. But when you are non-dimensionalizing it, okay, when you are
Yes,
non-dimensionalizing
sir.
it, the physical meaning is only associated with the term Reynolds number, not with the non-dimensional parameters.
Okay.
Clear?
Yes, sir.
Okay, fine. Next part is, I think this part is already answered. What is the physical meaning of the scaling parameters that are used in the non-dimensional seed? The scaling parameters, now these are all the terms that were being used. Now here one extra term is there, F. Now why this characteristic frequency? Sometimes in some cases, uh, there may be some vortex induced flow effects may be there. Okay, vortex induced flow effects which may give rise to vibration. So whenever there is a vibration, there is a periodic length. So how you choose the scaling parameters, that is again something like the part that we have discussed just earlier to that. Correct, it is just like the characteristic length. Okay, you need to first of all
So
decide.
it is.
Huh?
So which parameter is very important? We take that and use as a scaling parameter.
Yes, we use that
Like
as a scaling
in
parameter.
case of length or even diameter, length, width, whatever may be, we use only that characteristic length L as the reference
Exactly.
parameter.
Yes, reference.
But that parameter L might be of anything also.
Huh?
It might be of either diameter. For example, suppose you consider there's a duct-like geometry,
Huh?
rectangular duct.
Huh?
In that case, we have length, width, and then what height also.
Okay.
Three
Huh?
parameters here.
Huh?
Now suppose now if you want to choose which one I have to choose a characteristic length in this case. That actually comes from the which is very important physically. For example, suppose I say I'm interested in and interested in understanding the flow only along the direction of the flow. For example, length.
Hmm.
Then length becomes my characteristic length, right? Now if
Yeah.
then if I want to non-dimensionalize that width and height, I have to use this length only.
It's length only.
Like that, it's correct. Okay.
Yes. Or sometimes
Okay.
somebody may like instead of considering length, somebody may consider the perimeter of the cross section, since it is a triangular duct.
Okay. Okay.
Yeah, it depends. Okay, it depends. You have to see
So
when
it's purely it's purely experience. Sometimes it's come from
experience.
experience
Yeah,
also.
yeah.
Okay.
It's purely
Getting.
experience. Yeah. So this is how you choose the scaling parameter. So I hope this part is clear.
Yes, sir.
Yeah. Now your next question.
Sir, before that, sir, sorry to interrupt.
Yeah, no problem,
Uh,
no problem.
hello, getting me,
Yeah,
sir.
yeah. I'm listening.
Sir, then how this cat you were just initially explained about nuts and factor, right? Nuts and
Knudsen number. Yeah.
that
Huh.
yeah, nuts and number.
Hmm.
How it is related to characteristic length? That
No,
is that
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 is
L.
that is not directly related to characteristic length. Means first of all, I explained Knudsen number just to make you to understand that like what is the importance of characteristic length, and then I answered your question.
So okay,
Yeah,
understood.
yeah.
So that is nowhere related to selection of that characteristic length.
No,
It's
no, no, no,
somewhat
no,
to
no,
explain.
no, no, no. That
Okay,
is no related to the selection. No, no.
okay.
Yeah. Yeah, what is the order of magnitude analysis? Order of magnitude analysis, again, this is related to your this thing, your non-dimensionalization of the equation. Okay, non-dimensionalization of the equation, how it is related. Suppose uh, I have a equation, say I'm writing a plus b equal to c. Okay, say this is a equation and a, b and c are some physical parameter. Okay, now if you compare these terms, now based on the principle of dimensional homogeneity, a, b and c, if it is a if it represents some physical situation, they must be having the same units, right, from the principle of dimensional homogeneity. Clear?
Yeah, correct.
Yeah.
Additive terms will have same
Huh?
dimension.
Pardon?
All additive terms will have the same dimension.
Yeah, same dimensions. Yeah. Now suppose for this particular parameter, say a plus b equal to cd, suppose cd. Okay, so it will be more general. A plus b equal to cd. So a, b and multiplication of c and d are having the same dimensions, right?
Yes, sir.
Yeah. Now say I have a quantity q. Okay, say not q. Okay, not q. Let me take a general one, otherwise. Okay, say I have a quantity q, so don't confuse it with discharge. Okay, say I have any quantity q, any general quantity, okay, which is having the same dimension as that of a, b, or c into d, and say this
Okay.
particular q is the characteristic value of that particular physical quantity we are talking about. Fine.
Okay. Okay.
Yeah. So for non-dimensionalizing, what will you do? A by q plus b by q equal to cd by
C into D by
q.
Q.
Right?
Yes, sir.
Yeah. Now see, suppose the value of this is coming out to be, say, 1. Say the value of this is coming out to be 0.01, and the value of this is coming out to be, say, around say 10. Okay.
Okay.
Yeah. Now this non your question was, what is order of magnitude analysis? What is the order of magnitude? Now see, you are dividing all these quantities by a characteristic quantity, the value of a characteristic quantity. Okay, so the first term a by q is of the order of 1, b by q is the order of 0.01, cd by q is of the order of 10. So it gives you an idea that which parameter of this, or which terms of this equation the relative significance is more. Okay, so from this we can see that the relative significance of the term b is less in comparison to a and cd, and the significance of the term c into d is the highest. Okay.
Yeah, because it's higher in value.
Yeah, so this particular analysis is the order of magnitude analysis, and this is one another reason why we go for the non-dimensionalization of the governing equations. It gives you an idea basically which terms are more significant. Clear?
Okay. So simply we can eliminate terms without going to tedious
Yeah, you can eliminate
level.
terms. Yeah, that will not give you, means maybe in some situations it will not give you the exact solution, but sorry, but sometimes, yes, if you are doing the analysis in terms of the order, for example, uh, in some situations of boundary layer theory, this order of magnitude of analysis has proved to be very useful. Okay, so you can ignore or neglect some terms whose significance is very less. Okay, Ragul?
Yes, sir.
Yeah, is it okay?
Yeah. Okay, sir.
Yeah, fine. Yeah, your next answer, explain the direction in which the drag force will act for the following cases. Okay. So before I explain this, there are two things that I would like to clarify. First of all, you have understood what is drag force, right?
Yes, sir. I have a little bit doubt with that itself, sir.
Yeah. See, drag force is basically, again, it will be good if I be able to get a diagram. Force. Hmm. Yeah. Let me say, yeah, this is a simple diagram. Anyways, this diagram is visible, right, Ragul? Ragul?
Yes, sir.
Yeah, this diagram is visible.
Yes, sir. Yes, sir.
Yeah. Now see, say this is a body, a particular body. This is the flow direction. Now drag is the force which is acting along the flow direction. Clear?
Yeah. Yes, sir.
And lift is vertical to the flow direction or normal to the flow direction.
Yes, sir.
That is the simplest explanation, right?
Yeah, but that will be acting in.
Hmm.
But some definition says that it will act in a direction
Hmm.
opposite to the relative motion of the
That
fluid.
I will come to. Yeah,
That
I have understood your doubt.
uh,
That I will come to. Don't worry about that.
yes,
What is relative? Yeah, no, that was the second part. I told you, no, before that we'll have to discuss something about. Yeah. So the next part is relative velocity. Now, how do you conceive relative velocity?
we take some frame of reference
Okay.
and we find the relative velocity.
Suppose there are 2 points. Say I'm calling one point P, another point is Q, suppose. Okay. And say, let's don't give direction right now. Okay. Let's don't give any direction. So this is a point P. Here the magnitude of velocity is Vp. Here the magnitude of velocity is Vq. Okay. Fine.
Yes, sir.
Yeah. Now let us give a direction. Say P is moving, say Vp is along this direction. Say Vq is also along this direction. Fine.
Yes, sir.
Now relative velocity may be velocity of point P with respect to Q, and another is velocity of Q with respect to point P. Okay.
Yeah.
Yeah. So what will be the value for VPQ?
Vp minus Vq.
VP minus VQ. Yeah. So it is VP minus VQ, but these are all in vector forms. Okay. Means here the magnitude as well as the direction is important, and VQP is VQ minus VP. Clear?
Yeah. Yes, sir.
Yeah. Now see, now this is just an equation. Now this is a mathematical form, but very important is you have to understand. So for that you have you have given a very good situation here. You have sorry, you have given me 4 situations. Okay, so let's discuss this situation one by one. What is the first situation? The first situation is there is a particle inside a pipe which is moving at a speed of 3 meter per second, and the fluid is flowing at a rate of 4 meter per second, right?
Yes, sir. Yes, sir.
Yeah. Now see, you only have given a situation. V is the speed of the object relative to the fluid.
Yeah. Yeah.
Speed of the object relative to the fluid. Okay. So speed of the object, you just assume that you are this object.
Yes, sir.
You are moving along this direction at a speed of 3 meter per second, and the air surrounding you is moving at a rate of 4 meter per second. Okay.
Yes, sir.
Now please try to visualize what will be your speed relative to the fluid. Means your speed relative to the fluid means if you consider the speed of the fluid as the benchmark or as a reference. I'm not talking about the frames of reference. Okay. I'm simply saying if you measure your speed or if you observe your speed with respect to the speed of the fluid.
Object.
Hmm.
It will be minus 1 meter per
Minus
second.
1. Yeah. You will feel as if you are moving along the, see, you are moving at 3 meter per second. The, say, forget fluid. Say you are moving at 3 meters per second. I am moving at 4 meter per second. Okay. Both of us started, both of us, say you are Ragul R and I am Shubhranshu S. You are moving at 3 meter per second. I am moving at 4 meter per second. Okay. Say both of us started from this starting line. So in 1 second, you will cover 3 meter. I will cover 4 meter. Right?
Yes, sir.
Yeah. So if I will cover 4 meter, how will you feel? You will feel that you are moving backwards by 1 meter per second. Is not it? Physically, if you think
Yes, sir. Yes,
with respect to you. Okay. Is it
yes, sir.
clear?
Yes, sir. Yes, sir.
Yeah. So directly now you can see velocity of the object with respect to that of fluid will be velocity of the object which is 3 meter, and velocity of the object is 4 meter per second, and they both are in the same direction. So 3 minus 4, it will be minus 1 meter per second. Okay, so it will appear as if it is moving along this direction. Okay, is it clear?
Yeah, yes, sir, yes, sir.
This is positive direction, so if it is coming as minus 1 meter per second, then it is along your, this is your x-axis, say this is your positive x-axis, so this is moving along your negative x-axis, right?
Yes, sir, yes, sir.
Yeah. Now there is one more, means the same thing can be analyzed in a different way. How it can be analyzed in a different way, you see? Now I am drawing the same pipe that you have drawn. This is the object, it is moving at 3 meter per second and the fluid is flowing at 4 meter per second, right? Hello, Ragul?
Yes, sir.
Yeah, am I audible?
Yes, sir.
Yeah.
Breaking, voice is breaking up.
Am I audible now?
Yeah, yes, sir.
Yeah. So this particular this is the same situation that you have given me. It is moving at 3 meter per second and the fluid is moving at 4 meter per second, right?
Yes, sir.
Yeah. Now suppose you want to bring this body at rest. Huh?
Okay.
Mm, what will you do? You will impose a velocity along this direction,
Yeah, yeah.
3 meter, right?
Yes, sir.
Same for fluid. So that is, but I think the easiest way of analysis is the one that we have explained in the first part. Clear?
Yes, sir. Yes, sir.
Yeah. So I hope this part is also clear, your last part. And the rest situations are,
Yes,
see,
sir.
in this case it is 5 meter per second, this is 4 meter per second. So in this case, what will be the relative velocity of the object with respect to that of the fluid? Your second case, relative velocity of the object
Yes,
with
sir.
respect to fluid. Say you are considering this as the negative direction. So your velocity of the object is minus 5, right?
Yes, sir. Yes, sir.
And minus 4.
Yeah.
Clear? Is it clear?
Yes, sir.
Huh. So this is the thing. So I hope your doubts are clear.
Yes, sir.
Yeah.
Yes. Uh,
Yeah, tell me.
Hello.
Yeah, hello. I'm listening. Yes, Ragul.
Yes, sir.
Yeah. So your doubts are clear, right?
Yes, sir. Yes, sir.
Yeah, fine. So next, let me move to very fast because not much time is left. Whatever was supposed to be discussed today. Okay.
Okay, sir.
Yeah. So basically, the week 12 of this course on fluid mechanics, this live session was basically based on the concept of open channel flow and drag and lead force, that is flow past love bodies. So I'll be definitely providing the PDF version of this particular presentation, but you need to
Okay.
understand that there are few important topics that from which you need to practice some problems. For example, the first problem that I have given here is for uniform flow in open channel. So there are two very important equations, Chage's equation and Manning's equation. There are lot many problems considering different cross-sectional shapes of the open channel. So you please solve some problems. Then
Okay, sir.
the next problem is that of the vertical velocity distribution. Okay. So
Okay.
it was basically, it is a proof. Okay, I'm not discussing the problem, I'll be sharing this PDF. Okay, so
Okay,
definitely
sir.
you
Okay,
have access to all the course materials, so no problem with that.
sir. Okay.
Then you have to show that the vertical distribution of velocity is parabolic for uniform laminar flow in a wide open channel with constant slope and depth of flow. Now, what is a wide open channel? Can you tell me what is a wide open channel? A wide open channel is one where the width of the channel is much
Very large compared to length.
the depth,
Okay. Depth.
right? Yeah, the width of the channel is much greater than the depth of the channel. So again, this is a very interesting proof. You can follow any standard book, and again you can follow this text also. So one very standard book on fluid mechanics, other than your FM White or Sanjal and Simbala, they are definitely very good books, but there is one very good by Professor SK Som Vishwas. So there you will find ample of problems which are very much conceptual in nature. So please practice those problems. You'll be
Okay.
having a like a good exposure to the concepts. Then very important concept is of specific energy, that is the critical flow conditions in open channel, then hydraulic jump. Okay, so all these concepts are very important, and you need to practice some problems from these concepts as well. So you can take any. Then the problems on this flow path block bodies from drag and lift force. So just now we have seen, just now in with respect to your doubts, we have seen that what are the expression for drag force and lift force. Okay, so again these problems are very important. So one very important problem is that of terminal velocity. Maybe terminal velocity of a sphere that is falling through a fluid, maybe a raindrop falling through air. So it's a very simple problem. So you first of all need to look at the derivation, and then you need to solve the problem. What I will suggest is, don't directly try to memorize the equations or the formula. You first of all try to understand the derivation. It is a very simple thing. Suppose there is a drop which is
It's a
falling,
force
the,
balance. I
yeah,
understood.
force balance. So directly on the basis of force balance, you will be able to get the answer. And similar problem based on this. See, a car has a frontal projected area of 1.6 meters square and it travels at 60 kilometer per hour. It has a drag coefficient of 0.35 based on the frontal area. Calculate the power.
Okay.
So how do you calculate power? Power is the rate of work done. So basically force
Force
into
into velocity.
velocity. Yeah. So it's
Velocity.
very simple. Velocity you can calculate, or sorry, velocity is given to you. So force you can calculate from the drag force formula. So that way you can calculate power. And from power, the second part is, if the drag coefficient is reduced, means if CD value is reduced, what will be the next like the possible speed. Okay, so these are very simple problems from this chapter, and definitely from open channel flow you can expect many good questions in your competitive exam. So Ragul, I would like to know, what are you studying? Like, are you still in BTech or you have completed BTech?
Yes, sir. I completed BTech, sir.
Okay, in which specialization?
Chemical engineering.
Chemical engineering. Okay, great. So what are you doing now? Are you working somewhere or you are preparing for some exam?
No, sir. I'm preparing for exams. Gate. I'm preparing.
Gate you are preparing. So when did you pass your, like, completed your BTech class, this year?
No, sir. 2021 itself. I done, sir.
2021 you have passed, and now you'll be appearing for the gate. Okay, fine. All the
Yes,
best.
sir.
All the best. So you are
Okay.
appearing from chemical engineering, like gate chemical engineering paper, right?
Yes, sir. Yes, sir.
Okay. All the best. All the best.
Thank you.
And you
Thank you.
have my mail ID in case of any problem in the future. Like, see, this live session is over today. This was the last week.
Yes, sir.
But in case of
Yes, sir.
any like anything to discuss, because if you need any sort of help or any sort of clarification, you can always mail me. No problem. That'll be great.
Sure, sir. So
Okay.
finally, one doubt, sir.
Yeah,
One
yeah, yeah,
only small
yeah.
doubt.
Fine.
Sir, suppose you have container containing water, sir,
Okay.
and suppose I take one balloon that is free surface only. I take one balloon and I have to immerse the balloon into the water. From free surface, it has to be immersed to a distance of 10 meters, like that.
Okay. So here you have immersed a balloon which is at a distance of 10 meter from the free
10
surface.
meters.
Okay.
Yeah. How much amount of force I have to apply on the balloon so that it will be always in the immersed position. From the
How
top, I
much?
have to
How
apply
much?
certain
But I'm not getting your
force
voice
that is to
properly.
be applied.
Hmm.
Magnitude of the force that
Hmm.
is to be applied on the balloon so
Hmm.
that it will be submerged at a distance of 10 meter.
Okay. Means it will not move. That is the thing, right?
Yeah. What is the Just only the forces that is acting on it, sir. You describe about that only. What is the
What is the force required, right?
force? Force balances
Yeah,
around that balloon. That's all.
yeah, fine. If you consider this balloon, say this is the balloon, it is inside this thing, okay, and say what are the forces that are acting. One is definitely the weight of the balloon, right?
Yes, sir.
Yeah,
Yes, sir.
so one is definitely the weight of the balloon, the other one is the buoyant force,
By and
okay,
force.
but you have imposed one additional condition that it has to like it has to be here, it has to stand here at a distance of 10 meter, right?
Yeah.
Okay,
Yes, sir.
so if you want to keep it like that, if you want to keep it at a distance of 10 meters, so it is equivalent to a case where say you have chained the balloon, okay, maybe to the, you have chained the balloon to the bottom, suppose a hypothetical situation, okay,
Okay.
yeah. Now if you have chained the balloon, say there is a, if this is 10 meter means you know the total length of the container, right? The total length or the total depth
Yes,
of the
sir.
container, this is 10 meters, so the remaining is, say, I'm just writing L1, okay,
Okay.
yeah. Now the balloon is trying to move upward, the chain will try to bring down the balloon to the downward position, and as a result of this there will be, the balloon will be in this position, right? So basically the tension is also acting in the, or this force that we are calling, say I'm calling it Ft, will be in the downward direction only. Clear?
Yes, sir.
Yeah.
Yes, sir.
Now Fb, the buoyant force, that will depend upon the volume of the fluid displaced, so it is basically related to the volume of the balloon is equal to the weight of the
Okay, sir.
balloon. Huh.
I understood, sir, that FP should be equal to W plus FT.
Yeah, yeah, yeah. Huh.
But why don't you consider the weight of the liquid above the balloon? That is the 10 meter.
Pardon?
There is weight of certain column of liquid is resting above the balloon, right? Above the balloon, certain column of weight is resting. That
Yeah,
is 10
means you are
meter.
talking about the
Uh,
overburden, right?
yes, sir.
Yeah. See, why you are not considering the weight, that is, see, initially when there was no balloon, right? There was only fluid. Okay, there was
Okay.
only the fluid. Okay. Now, what is the only force that is there? It is the, it is what? What
Pressure
is the
force.
only force that is acting other than, there is the, there is definitely the weight of the fluid. Okay. There is definitely the weight of the fluid. Other than the weight, it is the pressure.
Yes, sir.
Pressure at different level, okay, pressure at different level. Now
Yes, sir.
when you are putting the balloon here, ideally speaking it is fine, that what you are telling, that you have to take the weight of the fluid that is above the balloon, okay, the weight of the fluid that is above the balloon. So if you, sorry, weight of the fluid that is, yeah, weight of the fluid that is above the, but when you are calculating the buoyant force, okay, just think carefully, when you are calculating the buoyant force, huh,
Yes,
hello,
sir.
yeah,
Yes, sir. Yes.
yeah, don't you think that the effect of that overburden is already taken into account? Please think
The
carefully.
binds itself due to pressure.
Buoyant C
Okay, okay.
is, yeah, one explanation is it is because of pressure it is acting fine. But don't you think in that the effect of what you are telling is already taken into consideration?
Mm, no, sir.
You're not getting. Okay,
Yeah.
fine. Acha, Ragul, is it okay like if we set some other time? Actually, now I have an appointment with the doctor. As I told you, I'm not
Okay.
feeling well.
Okay.
Okay.
Okay. Okay,
Yeah.
sir. No problem. No
So
problem.
yeah, yeah. I will get back to you. Don't worry. I have your mail ID also because you have sent me that mail. No.
Okay, sir. No problem. No problem.
Yeah, 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 yeah. I'll get back to you
Thank
with
you.
this. Yeah,
No problem.
yeah. Thank you.
Thank you.